Werner Heisenberg did more than make a quantitative statement when he said that the particle's position and momentum could not be known simultaneously. He wrote an equation that quantified the relationship. Let's see how that information can lead to an easy understanding of the hydrogen atom described in exquisite detail by the Schrödinger equation. Without going into too much detail, let's look at a proton and an electron. Since the electron has a very tiny mass, it can occupy a very large region of space. Conversely, the proton has a very large mass, 2,000 times that of an electron, and therefore it occupies a very tiny region of space. The result is a quantum mechanical hydrogen atom, a tiny massive nucleus surrounded by a much larger cloud representing the electron. If we look at a simple graph relating the probability of finding the electron in a shell at a given distance from the nucleus, we find that as we travel outward from the nucleus, the probability increases at first as the shell expands. It reaches a maximum value and then decreases again as the electron cloud thins to almost nothing at large distances. Amazingly, the radius where the probability reaches a maximum is precisely equal to the radius of the first allowed orbit of Niels Bohr's model of the hydrogen atom. And its energy is exactly equal to the energy of an electron in this orbit in the Bohr atom. So this is a very good picture of a hydrogen atom with an electron in the lowest energy state. The electron occupies a cloud instead of an orbit, but it spends most of its time at the radius predicted as an orbit by the Bohr model. It also spends most of its time possessing the energy that an electron in that orbit would have.